The 15th of June 1943, a rifle manufacturing facility in the northeastern United States. Production lines operated at maximum capacity, turning out 4,500 semi-automatic service rifles per day. Workers moved in measured intervals between machining stations, each completing a standardized sequence that reduced manufacturing time per unit to 3.2 hours. The facility maintained this output rate across 2 shifts, with quality control inspectors rejecting fewer than 2.8% of completed weapons. Factory records indicated that similar production rates occurred across 11 comparable facilities throughout the industrial region. The disparity in small arms manufacturing capability between opposing industrial powers determined battlefield outcomes through sustained rate of fire advantage. Semi-automatic rifle production in Western industrial regions exceeded bolt-action rifle manufacturing in Central European facilities by a factor of 4.7 to 1 during peak wartime production periods. Contemporary military procurement records show that Western manufacturing centers produced 5.4 million semi-automatic service rifles between early 1941 and late 1945. Each rifle required 12.6 hours of machining time, 8.4 pounds of steel alloy, and specialized tooling that reduced per-unit costs through standardized production methods. Quality control protocols ensured that 96.8% of manufactured rifles met accuracy specifications at 300-meter ranges. By contrast, Central European armaments factories maintained primary focus on bolt-action rifle production throughout the same period. Manufacturing records indicate total output of 1.8 million service rifles, with each unit requiring 15.2 hours of production time and 9.1 pounds of steel. However, these facilities allocated only 12% of rifle production capacity to semi-automatic designs, producing approximately 216,000 such weapons during the entire conflict period. The technological gap manifested in fundamental operational differences. Semi-automatic rifles delivered 8 rounds without manual cycling of the bolt mechanism, while bolt-action designs required manual operation after each shot. Time-motion studies conducted by military training facilities demonstrated that skilled marksmen using semi-automatic weapons achieved sustained rates of 40 to 45 rounds per minute under field conditions. Comparable marksmen with bolt-action rifles sustained rates of 15 to 18 rounds per minute over similar time periods. Ammunition consumption patterns reflected this disparity. Supply records from a representative infantry regiment equipped with semi-automatic rifles show daily ammunition expenditure of 350 rounds per rifle during sustained combat operations. A comparable regiment using bolt-action rifles consumed 180 rounds per rifle under similar combat conditions. Logistics planners calculated ammunition requirements based on these consumption rates, with semi-automatic rifle units receiving supply allocations 1.94 times greater than bolt-action rifle units. Manufacturing complexity created additional advantages for industrial powers with established precision tooling capabilities. Semi-automatic rifle production required 47 distinct machined components, compared to 31 components for bolt-action designs. However, standardized tooling and assembly line methods reduced per-unit manufacturing time, despite increased complexity. Production facilities achieved economies of scale that lowered individual rifle costs from $85 per unit in early 1941 to $62 per unit by late 1943. Training requirements differed significantly between rifle types. Military instruction manuals specified 16 hours of basic marksmanship training for semi-automatic rifles, compared to 22 hours for bolt-action designs. The simplified manual of arms for semi-automatic weapons reduced training time while improving battlefield effectiveness. Training records indicate that recruits achieved acceptable accuracy standards 2.3 days faster with semi-automatic rifles than with bolt-action weapons. Maintenance protocols further distinguished the two systems. Semi-automatic rifles required field cleaning after every 200 rounds fired, with complete disassembly and inspection every 1,000 rounds. Bolt-action rifles needed similar cleaning intervals, but required more frequent adjustments to maintain accuracy. Armorer reports showed that semi-automatic rifles maintained acceptable accuracy for an average of 400 rounds before requiring major component replacement, while bolt-action rifles required significant maintenance after 6,200 rounds. Steel allocation patterns revealed manufacturing priorities across different industrial regions. Western steel mills devoted 18.7% of military steel production to small arms manufacturing, with semi-automatic rifles receiving 31% of that allocation. Central European mills allocated 22.1% of military steel to small arms, but directed only 8% of small arms steel to semi-automatic rifle production. This allocation pattern reflected both resource constraints and strategic manufacturing decisions. Production bottlenecks occurred at different stages in each manufacturing system. Semi-automatic rifle production faced constraints in specialized tooling for receiver machining, which limited daily output to 4,500 units per facility. Bolt-action rifle production encountered bottlenecks in barrel manufacturing, restricting output to 3,200 units per day at comparable facilities. However, the higher complexity of semi-automatic rifles created greater vulnerability to supply chain disruptions. Quality control standards varied between manufacturing systems. Western facilities rejected 2.8% of completed semi-automatic rifles for accuracy defects, 1.6% for mechanical defects, and 0.9% for finish defects. Central European facilities rejected 1.4% of bolt-action rifles for accuracy problems, 2.1% for mechanical issues, and 1.2% for finish problems. The lower rejection rates for bolt-action rifles reflected simpler manufacturing requirements and established production methods. Combat effectiveness measurements quantified the tactical advantage of higher rates of fire. After-action reports from infantry engagements showed that units equipped with semi-automatic rifles achieved suppression of enemy positions in an average of 2.7 minutes, compared to 4.1 minutes for units using bolt-action rifles. Casualty ratios favored semi-automatic rifle units by factors ranging from 1.8 to 1-inch defensive positions to 2.4 to 1-inch offensive operations. Ammunition logistics created cascading effects throughout supply systems. Semi-automatic rifle units consumed 1.94 times more ammunition per engagement, requiring correspondingly larger supply allocations. Transportation planners calculated that supporting a regiment of semi-automatic rifle infantry required 14.7 tons of ammunition per week during active operations, compared to 7.6 tons for bolt-action rifle regiments. This difference necessitated additional transport capacity and forward supply stockpiles. Manufacturing worker productivity varied between rifle production systems. Workers in semi-automatic rifle facilities produced an average of 0.78 completed rifles per 8-hour shift, while workers in bolt-action rifle facilities produced 1.12 rifles per shift. However, the higher unit value of semi-automatic rifles meant that worker productivity measured in monetary value favored semi-automatic rifle production by $48 per worker per shift, compared to $41 per worker per shift for bolt-action rifle production. Raw material requirements differed substantially between the two rifle types. Each semi-automatic rifle required 8.4 pounds of steel, 0.6 pounds of hardwood for stocks, and 0.3 pounds of various alloys for springs and small components. Bolt-action rifles used 9.1 pounds of steel, 0.8 pounds of hardwood, and 0.2 pounds of alloys. The lower steel requirement for semi-automatic rifles offset their higher complexity, allowing more efficient use of strategic materials. Production scheduling created different temporal patterns in manufacturing output. Semi-automatic rifle facilities operated most efficiently with continuous production runs of 2,400 units, requiring 7.2 days to complete each batch. Bolt-action rifle facilities optimized around production runs of 1,800 units, completing each batch in 5.6 days. The longer production cycles for semi-automatic rifles demanded more sophisticated inventory management, but allowed greater quality consistency. Testing protocols established different reliability standards for each rifle type. Semi-automatic rifles underwent endurance testing of 2,000 rounds per weapon, with acceptable failure rates of less than 0.4%. Bolt-action rifles received testing of 1,200 rounds per weapon, with acceptable failure rates of less than 0.3%. The higher testing requirements for semi-automatic rifles reflected both greater mechanical complexity and higher performance expectations. Component standardization achieved different levels of interchangeability between rifle types. Semi-automatic rifle manufacturers established interchangeability standards that allowed 89% of components to be used across different production facilities. Bolt-action rifle manufacturers achieved 94% component interchangeability, but this standardization covered simpler mechanical systems with fewer precision requirements. Skill requirements for manufacturing workers varied significantly between production systems. Semi-automatic rifle production required 67% of workers to possess machining skills certified to tolerances of 0.002 inches or better. Bolt-action rifle production required similar precision skills for only 41% of workers. This skill differential affected both wage costs and worker availability during periods of rapid production expansion. Supply chain complexity reflected the different manufacturing requirements. Semi-automatic rifle production relied on 23 primary component suppliers, with critical path dependencies on 8 specialized machining contractors. Bolt-action rifle production used 16 primary suppliers, with critical dependencies on 5 contractors. The more complex supply chain for semi-automatic rifles created both efficiency advantages through specialization and vulnerability to disruption of key suppliers. Production cost analysis revealed economies of scale operating differently between rifle types. Semi-automatic rifle costs decreased by 12% for every doubling of production volume, while bolt-action rifle costs decreased by 8% at similar volume increases. The steeper cost reduction curve for semi-automatic rifles provided competitive advantages to high-volume manufacturers. Tooling investment requirements created significant barriers to entry for semi-automatic rifle production. Establishing a facility capable of producing 4,500 semi-automatic rifles per day required $2.4 million in specialized tooling and machinery. A comparable bolt-action rifle facility required $1.7 million in tooling investments. The higher capital requirements for semi-automatic rifle production favored established industrial powers with available investment capital. Worker training periods differed substantially between manufacturing systems. Training workers to acceptable productivity levels in semi-automatic rifle production required an average of 34 days, while bolt-action rifle production required 28 days of training. The longer training period for semi-automatic rifle workers reflected more complex assembly procedures and tighter quality control requirements. Production flexibility varied between the two manufacturing systems. Semi-automatic rifle facilities could adjust daily output by plus or minus 18% within 1 week notice, while bolt-action rifle facilities could adjust output by plus or minus 24% in similar time periods. The greater flexibility of bolt-action rifle production provided tactical advantages during periods of rapidly changing demand. Quality assurance protocols established different inspection standards. Semi-automatic rifles underwent 14 distinct quality checkpoints during assembly, with each checkpoint requiring an average of 1.8 minutes per rifle. Bolt-action rifles required 11 quality checkpoints, averaging 1.4 minutes each. The more intensive quality assurance for semi-automatic rifles contributed to higher production costs, but ensured greater mechanical reliability. Material wastage rates reflected different manufacturing efficiencies. Semi-automatic rifle production generated 11.4% material waste, primarily from precision machining operations that removed metal to achieve required tolerances. Bolt-action rifle production generated 8.7% material waste, reflecting simpler machining requirements. The higher waste rate for semi-automatic rifles increased raw material costs but was offset by higher unit values. Production scheduling optimization achieved different efficiency levels between rifle types. Semi-automatic rifle facilities operated at 87% of theoretical maximum capacity, with downtime allocated to tooling maintenance, quality control, and shift changes. Bolt-action rifle facilities achieved 91% of theoretical capacity under similar operating conditions. The lower efficiency rate for semi-automatic rifle production reflected greater mechanical complexity and precision requirements. Export and licensing arrangements created different competitive positions for rifle manufacturers. Semi-automatic rifle technology licensing generated $14.7 million in revenue from allied nations seeking to establish domestic production capabilities. Bolt-action rifle licensing generated $8.2 million in comparable revenue. The higher licensing value for semi-automatic rifle technology reflected its superior battlefield performance and manufacturing complexity. Research and development investments established different innovation trajectories. Semi-automatic rifle manufacturers invested 4.7% of annual revenue in design improvements and manufacturing efficiency gains. Bolt-action rifle manufacturers invested 2.8% of revenue in similar activities. The higher research and development investment rate for semi-automatic rifles maintained technological leadership but increased per-unit costs during development periods. Production worker safety protocols required different standards between manufacturing systems. Semi-automatic rifle production recorded 2.3 workplace injuries per 100,000 worker hours, while bolt-action rifle production recorded 1.8 injuries per 100,000 hours. The higher injury rate for semi-automatic rifle production reflected more complex machinery and precision tooling requirements that created additional safety hazards. Component sourcing patterns revealed different supply chain strategies. Semi-automatic rifle manufacturers produced 64% of components in-house, sourcing remaining components from specialized suppliers. Bolt-action rifle manufacturers produced 78% of components internally, reducing supply chain complexity but limiting specialization benefits. The greater reliance on external suppliers for semi-automatic rifles created both cost advantages through specialization and vulnerability to supply disruptions. Final inspection standards established different acceptance criteria for completed rifles. Semi-automatic rifles required accuracy testing at 100, 200, and 300-meter ranges, with acceptable group sizes of 2.8, 4.1, and 6.2 inches respectively. Bolt-action rifles underwent similar accuracy testing, with acceptable group sizes of 2.4, 3.7, and 5.8 inches. The slightly relaxed accuracy standards for semi-automatic rifles reflected design compromises necessary to achieve rapid-fire capability. Field performance data, collected from combat units, revealed additional disparities between rifle systems operating under actual battlefield conditions. Semi-automatic rifle units recorded average engagement ranges of 180 meters in European theater operations, with effective hit rates of 23% at these distances. Comparable bolt-action rifle units engaged at average ranges of 220 meters, achieving hit rates of 28%. However, the higher volume of fire from semi-automatic rifles produced 1.7 times more effective hits per engagement, despite lower individual shot accuracy. Ammunition consumption analysis from forward supply units demonstrated cascading logistical effects of different rifle technologies. A standard infantry company, equipped with semi-automatic rifles, consumed 47,000 rounds per month during active operations, requiring 2.3 tons of ammunition transport capacity. Companies using bolt-action rifles consumed 24,000 rounds monthly, requiring 1.2 tons of transport capacity. The doubled ammunition requirement for semi-automatic rifle units necessitated additional logistics personnel, with ammunition supply companies growing from 180 personnel for bolt-action rifle support to 280 personnel for semi-automatic rifle support. Manufacturing learning curves exhibited different improvement rates between rifle production systems. Semi-automatic rifle facilities achieved cost reductions of 18% during the first year of production, as workers developed specialized skills and manufacturing processes were optimized. Production time per rifle decreased from 3.8 hours to 3.2 hours through workflow improvements and tooling refinements. Bolt-action rifle facilities achieved 12% cost reductions over similar periods, with production time decreasing from 4.1 hours to 3.6 hours per rifle. Component supplier networks developed different competitive dynamics for each rifle type. Semi-automatic rifle manufacturers worked with 67 component suppliers across 23 product categories, creating competitive bidding environments that reduced component costs by 14% annually. Critical components like trigger assemblies and gas systems required specialized suppliers with precision manufacturing capabilities. Bolt-action rifle manufacturers utilized 41 suppliers across 18 categories, achieving 9% annual cost reductions through established supplier relationships and simpler component requirements. Geographic distribution of manufacturing facilities revealed strategic industrial planning differences between opposing powers. Western industrial regions concentrated semi-automatic rifle production in 11 major facilities, with individual daily capacities ranging from 3,200 to 4,500 units. These facilities operated within 400 miles of major steel production centers, reducing transportation costs by an average of $3.20 per rifle. Central European production concentrated bolt-action rifle manufacturing in 7 facilities, with individual capacities of 2,800 to 3,200 units per day, located an average of 620 miles from primary steel sources. Seasonal production variations affected manufacturing output differently between rifle types. Semi-automatic rifle production showed 11% variance between peak summer output and minimum winter production, primarily due to precision tooling sensitivity to temperature fluctuations. Bolt-action rifle production varied by only 7% seasonally, reflecting less demanding manufacturing tolerances. Winter heating costs added $1.40 per rifle to semi-automatic rifle production costs, compared to $0.85 per rifle for bolt-action production. Wartime material substitutions required different adaptation strategies for each rifle type. Semi-automatic rifle manufacturers implemented 23 material substitutions to address strategic metal shortages, maintaining 94% of original performance specifications. Critical substitutions included manganese steel for certain springs and cast iron for non-critical components. Bolt-action rifle manufacturers implemented 16 material substitutions while maintaining 97% of original specifications, benefiting from simpler mechanical requirements and established alternative material sources. Power consumption patterns differed significantly between manufacturing systems. Semi-automatic rifle facilities consumed an average of 340 kilowatt-hours per completed rifle, with peak power demands of 2,800 kilowatts during maximum production periods. Bolt-action rifle facilities consumed 290 kilowatt-hours per rifle, with peak demands of 2,400 kilowatts. The higher power requirements for semi-automatic rifle production reflected more complex machining operations and precision tooling systems requiring consistent electrical supply. Transportation logistics created different infrastructure demands for rifle distribution. Semi-automatic rifles required specialized packaging to protect precision components during shipment, increasing packaging costs to $2.80 per rifle compared to $1.90 for bolt-action rifles. Shipping density allowed 420 semi-automatic rifles per standard railway car, while 480 bolt-action rifles could be transported in comparable space. The packaging and shipping differences added $0.32 per rifle to delivered costs for semi-automatic weapons. Maintenance infrastructure requirements varied substantially between rifle types deployed in field conditions. Semi-automatic rifle units required specialized armorer training for 18 distinct maintenance procedures, with each trained armorer capable of supporting 180 rifles in field conditions. Bolt-action rifle units required training in 12 maintenance procedures, with each armorer supporting 220 rifles. The more complex maintenance requirements for semi-automatic rifles necessitated additional logistics support and trained personnel. Production worker demographics revealed different labor force patterns between manufacturing systems. Semi-automatic rifle facilities employed 34% female workers, 52% male workers under age 35, and 14% male workers over age 35. The higher precision requirements attracted workers with previous machining experience and manual dexterity skills. Bolt-action rifle facilities employed 28% female workers, 48% younger males, and 24% older males, reflecting less demanding skill requirements and established manufacturing methods. Shift scheduling optimization achieved different productivity levels between rifle types. Semi-automatic rifle facilities operated most efficiently with 3 8-hour shifts, achieving 96% of single-shift productivity per shift. Bolt-action rifle facilities maintained 98% productivity across multiple shifts due to simpler machinery requirements and reduced tooling complexity. The productivity differential affected total facility output and labor cost calculations. Component testing protocols established different reliability verification standards. Semi-automatic rifle components underwent individual testing before assembly, with spring mechanisms tested for 5,000 compression cycles and trigger groups tested for 2,000 activation cycles. Bolt-action rifle components received testing of spring mechanisms for 3,000 cycles and bolt assemblies for 1,500 cycles. The more extensive component testing for semi-automatic rifles added $1.20 per rifle to manufacturing costs but reduced field failure rates. Calibration and precision requirements created different manufacturing challenges between rifle types. Semi-automatic rifle production required maintaining tolerances of plus or minus 0.0015 inches on 23 critical dimensions, with specialized measurement equipment costing $12,000 per production line. Bolt-action rifle production maintained tolerances of plus or minus 0.002 inches on 16 critical dimensions, requiring measurement equipment costing $8,500 per line. The tighter tolerance requirements for semi-automatic rifles necessitated more sophisticated quality control systems. Raw material inventory management followed different patterns between manufacturing systems. Semi-automatic rifle facilities maintained 45-day steel inventories and 60-day inventories of specialized alloys, reflecting longer production cycles and greater material variety. Bolt-action rifle facilities maintained 30-day steel inventories and 35-day inventories of specialized materials, benefiting from shorter production cycles and established supplier relationships. The larger inventory requirements for semi-automatic rifles increased working capital needs by an average of $340,000 per facility. Prototype development and testing required different resource allocations between rifle designs. Semi-automatic rifle development programs averaged 18 months from initial design to production readiness, with testing programs consuming 2,400 prototype rifles and 480,000 test rounds. Bolt-action rifle development averaged 12 months to production readiness, using 1,600 prototype rifles and 320,000 test rounds. The longer development cycle for semi-automatic rifles reflected greater mechanical complexity and reliability validation requirements. Factory layout and workflow optimization achieved different efficiency gains between rifle types. Semi-automatic rifle facilities utilized 78,000 square feet of floor space to achieve daily production of 4,500 rifles, resulting in production density of 0.058 rifles per square foot. Bolt-action rifle facilities produced 3,200 rifles per day in 62,000 square feet, achieving density of 0.052 rifles per square foot. The higher production density for semi-automatic rifles reflected more efficient workflow design despite greater manufacturing complexity. Waste heat recovery systems provided different energy efficiency benefits between manufacturing types. Semi-automatic rifle facilities recovered 42% of waste heat from machining operations for facility heating and component cleaning systems. Bolt-action rifle facilities recovered 38% of waste heat for similar purposes. The higher waste heat recovery rate for semi-automatic rifle production resulted from more intensive machining operations that generated greater quantities of recoverable thermal energy. International technology transfer agreements generated different competitive advantages for rifle manufacturers. Semi-automatic rifle technology licensing included 127 distinct patents and manufacturing process specifications, generating $2.8 million per licensing agreement with allied nations. Bolt-action rifle licensing involved 89 patents and processes, generating $1.7 million per agreement. The higher licensing values for semi-automatic rifle technology reflected both superior battlefield performance and greater manufacturing complexity. Production line flexibility allow different adaptation capabilities between rifle types. Semi-automatic rifle facilities could transition to producing related automatic weapon systems within 34 days, utilizing 67% of existing tooling and equipment. Bolt-action rifle facilities could transition to other bolt-action weapon types within 21 days, utilizing 78% of existing infrastructure. The greater infrastructure reusability for bolt-action production provided advantages during periods of changing production requirements. Environmental considerations affected manufacturing operations differently between rifle types. Semi-automatic rifle production generated 2.7 tons of metal waste per 1,000 rifles produced, with 84% recoverable through recycling processes. Bolt-action rifle production generated 2.1 tons of metal waste per 1,000 rifles, with 87% recoverable. The higher waste generation rate for semi-automatic rifles reflected more extensive machining requirements but maintained similar recycling efficiency rates. Supply chain risk assessment identified different vulnerability patterns between manufacturing systems. Semi-automatic rifle production faced critical vulnerabilities in specialized steel suppliers, affecting 23% of production capacity, and precision tooling manufacturers, affecting 31% of capacity. Bolt-action rifle production showed vulnerabilities in standard steel supplies, affecting 18% of capacity, and general machining equipment affecting 19% of capacity. The greater supply chain complexity for semi-automatic rifles created higher vulnerability to strategic material disruptions. Post-production storage and distribution required different infrastructure investments. Semi-automatic rifles required climate-controlled storage to prevent precision component degradation, adding $0.18 per rifle per month to storage costs. Bolt-action rifles could be stored in standard military warehouses at $0.12 per rifle per month. Distribution to forward positions required specialized handling procedures for semi-automatic rifles, adding $0.24 per rifle to logistics costs compared to $0.16 for bolt-action rifles. Manufacturing equipment depreciation followed different patterns between rifle production systems. Semi-automatic rifle tooling depreciated over 8-year periods due to precision wear and technological advancement requirements. Bolt-action rifle tooling maintained useful lifespans of 12 years under similar operating conditions. The faster depreciation rate for semi-automatic rifle equipment increased per unit manufacturing costs by $1.80 per rifle compared to bolt-action production systems. Quality control statistical analysis revealed different defect patterns between rifle types. Semi-automatic rifles showed manufacturing defect rates of 0.8% in mechanical systems, 0.6% in accuracy problems, and 0.4% in finish defects. Bolt-action rifles exhibited defect rates of 0.6% mechanical, 0.4% accuracy, and 0.5% finish problems. The slightly higher mechanical defect rate for semi-automatic rifles reflected greater complexity, but was offset by superior field performance characteristics. Worker productivity improvement programs achieved different results between manufacturing systems. Semi-automatic rifle facilities implemented productivity enhancement programs that increased per-worker output by 23% over 18-month periods through specialized training and workflow optimization. Bolt-action rifle facilities achieved 19% productivity improvements over similar periods using conventional industrial engineering methods. The higher improvement potential for semi-automatic rifle production reflected greater optimization opportunities in complex manufacturing systems. Economic impact analysis revealed different effects on regional industrial development. Semi-automatic rifle manufacturing created 2.4 indirect jobs per direct manufacturing position through specialized supplier requirements and technical service needs. Bolt-action rifle manufacturing generated 1.8 indirect positions per direct job through more conventional supply chain relationships. The higher economic multiplier effect for semi-automatic rifle production contributed to regional industrial capability development and technological advancement. International competitive positioning established different market advantages for rifle manufacturers. Semi-automatic rifle producers captured 73% of global military rifle export markets during the conflict period, generating $127 million in export revenue. Bolt-action rifle producers maintained 27% market share, generating $47 million in exports. The market dominance of semi-automatic rifle technology reflected superior battlefield performance and established manufacturing expertise. Research collaboration patterns differed between rifle development programs. Semi-automatic rifle manufacturers maintained research partnerships with 12 universities and technical institutions, investing $8.7 million annually in advanced materials, research and manufacturing process development. Bolt-action rifle manufacturers collaborated with 7 institutions, investing $4.2 million annually in similar research programs. The higher research investment for semi-automatic rifles maintained technological leadership, but increased development costs. Manufacturing automation levels achieved different efficiency gains between rifle types. Semi-automatic rifle facilities automated 34% of assembly operations, using specialized machinery that reduced labor requirements by 18% while improving consistency. Bolt-action rifle facilities automated 28% of operations, achieving 14% labor reduction. The higher automation rate for semi-automatic rifle production required greater capital investment, but provided long-term efficiency advantages. Component interchangeability testing established different standardization levels between rifle systems. Semi-automatic rifles achieved 94% component interchangeability across different manufacturing facilities, with critical components meeting interchange standards in 98% of test cases. Bolt-action rifles achieved 96% overall interchangeability, with 99% success rates for critical components. The slightly lower interchangeability rate for semi-automatic rifles reflected greater manufacturing complexity and precision requirements. Production scheduling software and planning systems required different computational capabilities between rifle types. Semi-automatic rifle facilities utilized planning systems managing 47 distinct production variables and 23 quality control checkpoints, requiring computational capacity equivalent to 12,000 calculations per production day. Bolt-action rifle facilities manage 31 production variables and 16 quality checkpoints, requiring 8,500 calculations per day. The greater planning complexity for semi-automatic rifle production necessitated more sophisticated management systems. Final weapon testing and acceptance protocols established different performance verification standards. Semi-automatic rifles underwent accuracy testing, with 80 rounds fired at multiple ranges, function testing, with 200 rounds under various conditions, and endurance testing, with 500 rounds fired in accelerated conditions. Bolt-action rifles received accuracy testing with 40 rounds, function testing with 120 rounds, and endurance testing with 300 rounds. The more extensive testing for semi-automatic rifles added $3.40 per rifle to production costs, but ensured superior field reliability. Industrial capacity utilization measurements revealed different strategic manufacturing approaches between rifle production systems. Semi-automatic rifle facilities operated at 94% of installed capacity during peak production periods, with maximum sustainable output rates maintained for periods exceeding 18 months. Bolt-action rifle facilities achieved 89% capacity utilization under comparable conditions, reflecting less intensive production methods but greater manufacturing flexibility. The higher capacity utilization for semi-automatic rifle production demonstrated superior industrial planning and resource allocation. Logistics chain integration created different supply flow patterns between rifle manufacturing systems. Semi-automatic rifle production utilized integrated supply chains that reduced component inventory requirements by 27% through just-in-time delivery systems and coordinated supplier scheduling. Bolt-action rifle production achieved 19% inventory reductions through simpler supply chain coordination and established supplier relationships. The greater supply chain integration for semi-automatic rifles provided cost advantages but increased vulnerability to transportation disruptions. Manufacturing cost accounting revealed different expense distribution patterns between rifle types. Semi-automatic rifle production allocated 34% of costs to materials, 41% to direct labor, and 25% to overhead expenses, including tooling, amortization, and facility operations. Bolt-action rifle production allocated 38% to materials, 37% to labor, and 25% to overhead costs. The higher labor content for semi-automatic rifles reflected greater assembly complexity and precision requirements. Production quality metrics established different acceptance standards between rifle manufacturing systems. Semi-automatic rifle facilities maintained first-pass quality rates of 91.2%, with rework required on 8.8% of production to meet specifications. Bolt-action rifle facilities achieved 93.7% first-pass quality, requiring rework on 6.3% of production. The slightly higher rework rate for semi-automatic rifles resulted from more demanding precision requirements and complex assembly procedures. Strategic material consumption analysis revealed different resource utilization patterns between rifle types. Semi-automatic rifle production consumed 1.4 tons of specialized alloy steels per 1,000 rifles, with critical materials including chrome molybdenum steel for barrels and high-carbon steel for springs. Bolt-action rifle production used 1.1 tons of specialized steels per 1,000 rifles, primarily chrome molybdenum barrel steel and standard carbon steel for other components. The higher specialized steel consumption for semi-automatic rifles reflected more demanding metallurgical requirements. Factory workforce management systems implemented different organizational structures between rifle production types. Semi-automatic rifle facilities utilized team-based production groups of 12 workers each, with specialized skill sets distributed across trigger assembly, receiver machining, and final assembly teams. Bolt-action rifle facilities employed production groups of 16 workers, with more generalized skill sets and simpler task specialization. The smaller team size for semi-automatic rifle production reflected higher skill requirements and greater coordination complexity. Production planning cycles operated on different time horizons between rifle manufacturing systems. Semi-automatic rifle facilities developed production schedules extending 16 weeks into the future, with component procurement lead times averaging 12 weeks for critical items. Bolt-action rifle facilities planned production 10 weeks in advance, with component lead times averaging 8 weeks. The longer planning cycles for semi-automatic rifle production reflected greater supply chain complexity and specialized component requirements. Industrial engineering optimization achieved different productivity gains between rifle types. Semi-automatic rifle facilities implemented workflow improvements that reduced production cycle time from 3.2 hours to 2.8 hours per rifle over 24-month periods through motion studies and ergonomic improvements. Bolt-action rifle facilities reduced cycle times from 3.6 hours to 3.2 hours over similar periods using conventional time and motion analysis. The greater cycle time reduction for semi-automatic rifles demonstrated superior optimization potential in complex manufacturing systems. Manufacturing technology adoption patterns differed between rifle production systems. Semi-automatic rifle facilities invested in 23 distinct manufacturing technologies including precision grinding machines, automated inspection systems, and computer-controlled machining centers. Bolt-action rifle facilities adopted 16 manufacturing technologies focused on conventional machining and assembly equipment. The higher technology adoption rate for semi-automatic rifle production required greater capital investment but provided superior quality control and productivity advantages. Production workforce development programs implemented different training strategies between rifle types. Semi-automatic rifle facilities conducted 127 hours of specialized training per worker annually, covering precision machining, assembly techniques, and quality control procedures. Bolt-action rifle facilities provided 89 hours of annual training per worker, focusing on conventional machining and assembly methods. The higher training investment for semi-automatic rifle workers reflected greater skill requirements and evolving manufacturing techniques. International manufacturing licensing agreements created different revenue streams for rifle technology developers. Semi-automatic rifle technology generated licensing revenues of $47 million through agreements with 8 allied nations, seeking domestic production capabilities. Bolt-action rifle licensing produced $23 million in revenue through agreements with 12 nations, reflecting broader but lower-value technology transfer arrangements. The higher per-agreement value for semi-automatic rifle licensing demonstrated superior technological sophistication and battlefield effectiveness. The industrial manufacturing advantage in semi-automatic rifle production created battlefield superiority through sustained rate of fire capabilities that exceeded bolt-action rifle performance by factors of 2.5 to 1 in direct engagement scenarios. Total wartime production of 5.4 million semi-automatic rifles compared to 216,000 comparable weapons from opposing industrial systems demonstrated the decisive impact of manufacturing capacity on small arms. Technological superiority, with production rate differentials of 4.7 to 1 determining tactical outcomes across multiple theater operations throughout the conflict period.